Pluto, once considered a planet in our solar system, now holds the status of a dwarf planet, yet it continues to intrigue astronomers and astrophysicists alike. Recent discussions, especially by renowned experts like Neil deGrasse Tyson and Michio Kaku, have reignited interest in Pluto, particularly with the startling possibility of a potential collision between Pluto and Neptune. How could such an event occur, and what consequences would it have for Earth? Is this just a far-fetched scenario, or is there something more to this potential cosmic disaster? Join us as we explore the possibilities of a Pluto-Neptune collision. Despite its reclassification, Pluto remains a fascinating object of study in the vast universe. Its orbit is unique compared to other planets in the solar system. Taking a staggering 248 years to complete one orbit around the Sun, Pluto's journey is slow and irregular, and since its discovery in 1930, it hasn't even completed a single full orbit. What makes Pluto's orbit even more intriguing is its shape and tilt. Unlike the nearly circular orbits of most planets, Pluto's path is highly elliptical and tilted at a 17 degrees angle to the ecliptic plane, which adds complexity to its orbital mechanics. One of the most perplexing aspects of Pluto's orbit is its crossing point with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune does. This raises the question, why hasn't Pluto collided with Neptune? The answer lies in the intricate gravitational interactions between the planets. When astronomers first began studying Pluto's orbit, they were puzzled by its eccentricity and unusual shape. However, they soon discovered that despite Pluto's orbit crossing Neptune's, the two planets never collide. This stability is due to a delicate gravitational dance between Pluto, Neptune, and the Sun. A phenomenon known as the three-body problem describes how three objects like Pluto, Neptune, and the Sun influence each other's motion through gravity. Essentially, it's like trying to predict the movement of these bodies based on where they started and how their gravitational pulls affect each other. A key element that keeps Pluto's orbit stable is something called resonance. Specifically, for every 2 orbits Pluto completes, Neptune completes 3. This resonance locks the two planets into a stable pattern, ensuring that even when Pluto crosses Neptune's orbit, the planets are always far enough apart to avoid a collision. Additionally, another phenomenon called orbital precession further ensures stability. This refers to the gradual shift in Pluto's orbit, causing it to remain above or below Neptune's orbital plane, preventing a direct impact. Another factor is the VZK wobbling, named after the scientists Zell, Kai, and others, who discovered how gravitational interactions between Pluto, Neptune, and the Sun create a stabilizing effect. This wobble helps maintain Pluto's orbit over long periods, despite its apparent unpredictability. These intricate gravitational relationships were further examined through simulations in the 1980s, which revealed that while Pluto's orbit may be irregular, it remains stable over the long term. The giant planets, such as Neptune, Jupiter, and Saturn, also play significant roles in maintaining Pluto's orbit. Jupiter, in particular, has a powerful gravitational pull that helps stabilize Pluto's path, keeping it on a steady course over millennia. Thanks to these stabilizing forces, Pluto's orbit remains secure, and the risk of a collision with Neptune seems unlikely. The study of these cosmic dynamics underscores the importance of understanding the complex interactions between celestial bodies. This knowledge helps us comprehend not only the behavior of Pluto but also the overall stability of our solar system. In the end, the case of Pluto serves as a reminder of the fascinating and often unpredictable nature of space. Despite appearances, the orbits of celestial bodies can be remarkably stable due to the delicate balance of gravitational forces. Ongoing observation and research are essential to deepening our understanding of the universe and our place within it. Through the study of objects like Pluto, we gain valuable insights into the workings of our solar system and beyond. A circle is an ideal representation of the peculiarities of orbital chaos, which alludes to the delicate dependence of a celestial body's orbit on its initial conditions. This is clearly illustrated in Pluto's case, where even small changes in its position or speed can drastically alter its long-term orbit. Digital simulations have been invaluable for scientists in understanding Pluto's movement through space. These simulations use complex mathematics to model how Pluto and other celestial bodies, like Neptune, influence one another. By tweaking small details in these models, astronomers can see how even tiny changes can lead to significant differences in Pluto's orbit over time. In the late 1980s, these simulations revealed an intriguing fact about Pluto's orbit. Although it has features like libration and orbital precession that help stabilize it, its orbit can still be unpredictable and unusual. A small difference in Pluto's position or velocity can cause its orbit to change dramatically within just a few years. Yet, despite this chaos, Pluto's orbit remains stable over long periods, such as billions of years. This suggests that Pluto's journey around the Sun, although seemingly erratic, has a hidden order to it. Predicting the movements of celestial bodies, especially those with unpredictable orbits like Pluto, is an immense challenge. The inherent volatility of these systems means long-term predictions are often filled with uncertainty. While mathematical models provide powerful tools for understanding and forecasting the future movements of celestial bodies, they also highlight the limitations of our predictive abilities. These models heavily rely on the accuracy of initial conditions, and even a slight mistake or distortion can lead to vastly different outcomes, making accurate predictions a daunting task. Pluto's case also reminds us of the ever-changing and dynamic nature of the universe. While we've made great strides in understanding space, it highlights how much more there is to learn. Studying the gravitational influences of giant planets on Pluto's orbit offers important insights into the broader dynamics of our solar system. It reveals how the position and presence of each planet can have a profound effect on the stability and trajectory of other bodies in the system. But why are leading astrophysicists raising concerns about a potential collision between Pluto and Neptune, despite all these stabilizing forces? Neil deGrasse Tyson, a renowned astrophysicist known for his role in reclassifying Pluto as a dwarf planet, offers an intriguing perspective on the mysteries of our solar system, particularly the curious case of Pluto. Tyson's viewpoint on Pluto's reclassification stems from our continually expanding understanding of the solar system. He sees the reclassification not as a downgrade, but as a significant shift in our understanding of the various bodies orbiting the Sun. Tyson's approach to celestial mechanics emphasizes continuous learning and change, viewing the complexity of orbits like Pluto's as a sign of how much remains to be discovered. Despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune suggest that we may still have many mysteries to uncover. The possibility of such an event raises intriguing questions about the dynamics of the solar system and challenges our traditional notions of planetary stability. The idea that two celestial bodies so different in nature could collide is both alarming and fascinating, especially considering their vastly different qualities. Pluto, located in the outer reaches of the solar system, is far from the major planets, while Neptune, a gas giant with a strong gravitational field, plays a significant role in Pluto's orbital stability. The potential consequences of such a collision would be immense, offering new insights into gravitational interactions and the evolution of the solar system. To understand the dynamics of a possible collision, one must first consider the composition and properties of both planets. Despite Pluto being classified as a dwarf planet, it contains a mixture of substances believed to be in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and its atmosphere is primarily composed of nitrogen, methane, and carbon monoxide. On the other hand, Neptune is a massive gas planet made mostly of hydrogen, helium, and other lighter elements, with a dense atmosphere. A collision between such disparate bodies would significantly affect their structure and behavior, potentially creating an event visible over vast distances. What makes this theoretical collision particularly captivating is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in maintaining Pluto's orbit, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, also has a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's territory. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune unlikely. However, despite these stabilizing factors, ongoing research has shown that the relationship between Pluto and Neptune is not as straightforward as a potential collision course. The gravitational resonance between the two planets, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3, creates a massive lock that prevents them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while intersecting in the vast expanse of space, have never resulted in a collision. In conclusion, while the possibility of a Pluto-Neptune collision raises fascinating questions about the dynamics of the solar system, the complex interactions between planets and their gravitational forces make such an event highly unlikely. These ongoing discoveries remind us how much we still have to learn about the vast and dynamic universe we live in.